right, so we'll get started here. Let me write it up here, theorem. So today we're talking about some theorems of integral complex calculus. So here, the first one we're going to do is complex Ftc One. And what that says in our version of it is let D be star-shaped domain. All right. And we'll let f of z be holomorphic on D, right? Then f of z has primitive on D given by f of z equals integral z naught to z f of zeta d zeta, where z naught is star center of D. All right. So this is the complex Ftc One. Don't worry, you didn't miss anything. I just wrote that. That's all I've done. I do need to remind myself to regrade your both your tests. I have them, but I forgot to grade them. So here it is. The proof is as follows. Okay, so if we can show that f of z, if we can show that f of zeta d zeta is a closed form, right? Then we have a theorem 3.2.10, which said that then the form was exact, and also it's well, anyway, basically use the closed implies exact theorem is essentially it. Okay, so here it is. F of z dz, all right, is u plus iv times dx plus I dy, all right? And of course that is equal to u plus iv dx plus iu minus v dy. So that's the form we're integrating, right? We're integrating that form. Well, that's the form we're thinking about. We're studying this form, right? F of z dz. So, by the way, what does it mean to say that f of z has a primitive on D up here, by the way? I should mention that. That means what? That means that df dz is what? It's equal to f, right? Df dz is equal to f, so it's the antiderivative. Primitive is another word for antiderivative. Okay, so anyway, just for the sake of discussion, this is P, right? This is Q, right? We're looking at this form P dx plus Q dy. And what can we say about that? Is this a closed form? It is a closed form, right? Since, let's see here, px, right? It's going to be py, rather. You could do qx. What do you want to do? Let's start with qx. Qx, the partial derivative of q with respect to x would be, right, I ux minus vx, right? But since f is holomorphic, we know the Cauchy-Riemann equations hold, right? So ux is equal to what? Vy. And what's Vx equal to? Vx is equal to minus Uy. So minus minus gives me plus Uy, right? But what is that? No, that's not Px. That's partial partial y of u plus iv, right? In other words, it's Py. So therefore, the form f of z dz is closed. We showed that it satisfies the definition of closed. It's closed on D, which implies it's exact. And what was the formula? Remember the formula for the potential? Our proof in theorem 3.10 was what? We could say, in other words, if this thing is omega, right, so omega is equal to dh. And how was the h, where h was what? H was the integral from z naught to z of omega, right? That was the proof, actually. That's how we constructed the potential for the closed form to show it's exact, which in our current language gives us that here. So we're calling h big F. So f of z is the integral from z naught to z of, what was it? Yeah, p dx plus q dy. But, and so the reason for the not writing, like the reason for the zeta up in here is because that's just, you know, this is even a little bit sketchy. Well, this is okay. It's not great. If I put z equals to x plus iy, it's bad. Because I really shouldn't use the same letter for a fixed point here as I'm doing the integration over. And that's why this is a better presentation of the idea. Because we're integrating from z naught to z, but the integration is over zeta. Right? Z is fixed here, whereas zeta is an integration variable. Anyway, that's Ftc One.
Oh, it's like the real sense it'd be like saying we're going from 2 to x.
Yeah, you know, well, I mean, so for example, in Calc 1, if you want to find the velocity at time t, you should integrate from 0 to t of like dx d tau. D tau. We introduced this tau to not conflate it with the t in Calc 1, if you're careful. If you're not careful, you just say, well, integrate from 0 to t of dx dt dt, you know, which you might find physicists doing at times, but, or lackadaisical calculus 1 instructors, whatever. Okay, next up. This is called, at least this is what, so Gamelin, you know, I don't know. Sometimes Gamelin is a little bit funny about how he labels theorems. So I always say, when it comes to Gamelin's labels of theorems, maybe take a second opinion. One of the quirks of Gamelin's text is he has a very low opinion of Gorsaw's theorem. And so he practically has removed it from the textbook and defined it away as a problem. He's just not interested in the discussion. We'll spend about 20 minutes, 30 minutes proving Gorsaw's theorem in here in a bit. Not today. So I'm just saying, be wary of Gamelin's labels for theorems. Anyway, here's the theorem. A continuously differentiable function f of z on D is holomorphic if and only if f of z dz closed. All right, so what's the proof of this? Well, I think we just proved half of this? Yeah. Didn't we just prove f of z dz is closed, right? So the forward implication just did. We just did that right here, right? That was this line. So how about the other direction? Suppose f equals to u plus iv, and, dz is dx plus I dy. So f of z dz is equal to, what was it? u plus iv dx plus iu minus v dy, right? Just setting it up. Suppose that's closed. Let me call this omega. Suppose omega closed. Then what does that mean?
Suppose it's closed.
Yeah, if this is a closed form,
Exact.
it's exact. That's true. Since this is star-shaped, that would imply that this is exact. That's true. But I'm trying to prove that it's holomorphic. I'm trying to prove that u plus iv is holomorphic, right? So check this out. So what I have is that partial y, right, of iu minus v is equal to partial x of u plus iv. This is what we mean by, this is our definition of closed. That the y derivative of the x component is equal to the x derivative of the y component. This is the closed condition. But what does this single complex equation give you?
It gives you Koshi.
I think it does, yeah, because this gives me minus I uy minus vy is equal to ux plus ivx, right?
Yeah.
Which gives me two real equations. The imaginary parts being matching gives me vx is equal to uy. And we also get what? Ux is equal to, wait a minute. What? That's not what I want.
Aren't you supposed to partial differentiate?
So is that the closed condition? What did I just do? I did the y derivative of the y component
Yeah.
equals the x derivative of the x component. That is, I flip-flopped it, didn't I?
Yeah.
So, thank you. Did that on purpose for your learning? That's just good pedagogy, right? No, actually not. If you do this, the students will say you don't know what you're doing, you make mistakes in class, and they will not give you the rating that you desire on the Rate My Professor. You'll be in trouble. Let's see here. So there you go. I was supposed to do that. And of course, once we do that, then we get ux equals to vy, right? And vx equals to minus vx equals to ui. And of course, these are the CR equations, right? Cauchy-Riemann equations. And given that we've assumed it's continuously differentiable, if we have continuous differentiability and the Cauchy-Riemann equations holding on a domain, that implies that, therefore, u plus iv is holomorphic on D. So there you go. That's Morera's theorem. So a closed, f of z dz is closed if and only if f of z is holomorphic. So, which just means f prime of z exists, right? Okay, that brings us to theorem. What's our next theorem here? I got all kinds of theorems for you today. Don't worry, we're going to do some calculations, though, too. So this is Cauchy's theorem. Here's what it says. D bounded domain. What's a domain? Nope. A domain is open and connected. It's the bounded domain with piecewise smooth boundary if f of z is holomorphic and continuously differentiable. On D, and extends continuously to the boundary of D, all right, then the integral on the boundary of D of f of z dz is 0. So what this says is that if your function has a complex derivative which exists inside the domain, right, and a little bit beyond the domain, all right, then guess what? The integral of that function is 0 if you go around the boundary. So let's see if we can discover the proof together. So what are we trying to do here? So let's assume, as it says in the theorem, that it's holomorphic, all right? And we want to integrate over the boundary of D, right, of what was it? F of z dz, which is what? U plus iv dx plus iu minus v dy, yeah? So we could use complex Green's theorem, right? Complex Green's theorem says that that's the double integral over D, right, of partial, what is it? Partial x of the q, which in this case is iu minus v, right, minus partial y of the u plus iv, right? But we just did this calculation, right? What is this? This is exactly px minus, it's qx minus py, right? In the language of the previous theorem. This is just straight up that qx we just did, and this is the py where I've just talked about it up there, right? And so we know that those are equal if what? If the Cauchy-Riemann equations hold, which of course they do since the function's holomorphic. So this is equal to that, so we're integrating 0, which of course gives us 0. And that's Cauchy's theorem. And of course, if you hadn't just done the previous theorem, it's a simple calculation anyway, right? You just take the partial derivatives and then apply the Cauchy-Riemann equations. Everything cancels. You get 0. So that's not bad, is it? All right. So let's look at an example. Example 4.3.3. Here we're looking at f of z equal to 2 over 1 plus z squared. All right. And I want to study the integral of that function over a couple different circles. All right. So you guys tell me, what's the domain? What's the domain of the function I just wrote here? You guys tell me.
Well, it can include the point -1.
I think -1's okay. That gives me 2 in the denominator.
Oh, yes, it does.
Put your hearts in the right place.
No, it should be real on the real axis line. It should be fine, and then anything on the imaginary axis. Oh wait, it doesn't give me -1i.
Okay, yeah. So,
The point 0i.
okay, so this is. Oh yeah, I is a trouble, isn't it?
Yep.
So this z squared plus 1 factors into z plus I times z minus I, right? So the domain of f of z is the complex numbers, and you got to remove minus I and I, right? But if I call that, if I call that D, right? I'll call that D, right? For the sake of discussion here. Surely f of z is holomorphic on D, right? Because as long as you avoid those 2 points, you can differentiate this, right? Quotient rule still makes sense. So like the derivative of f prime of z is just minus 4z over 1 plus z squared squared. All right, so definitely holomorphic. All right. So let's define a circle around I and a circle around minus I. All right, and let's look at circles of radius, say epsilon. All right, so and let's see, the label I gave these circles, I called it gamma epsilon of minus I. So this one would be like gamma epsilon of minus I. This one would be the circle of radius epsilon around I. I'm assuming that they're radius epsilon, yeah.
Are they not intersecting?
Not unless epsilon's bigger than 1. So, and I want to let those be counterclockwise, yeah. Okay. And I want to study the integral of f of z around these circles. Okay? So to do that wisely, we need to notice a little bit of algebra here. You guys remember partial fractions?
Like, yeah.
So, but yeah, f of z, or maybe differential equations.
Yeah, that's
So 2 over z plus I times z minus I. So we can rewrite that as like a over z plus I plus b over z minus I, right? So you guys, what are a and b then? Let's work it out. So we get 2 is a times z minus I plus b times z plus I. And if you plug in I, what do you get?
you get A is equal to B minus B, no, B 2I.
Yeah, 2ib. And if you plug in z equals to minus I, what do you get? Yeah, minus 2ia, right?
Yeah, A. Yeah.
So b is equal to 1 over I, also known as minus I, and a is equal to minus 1 over I, also known as I. Huh. So the partial fractions in my notes is bogus. I say f of z is equal to 1 over z plus I plus 1 over z minus I. That just is not the case, you know? Dang it. Oh, man. I'm surprised no one has pointed this out. I think usually what happens in this course is I just state with authority that f of z is equal to the sum of those two things, and I don't check it. Yeah? But, it is what it is, right? So, so we find is, so I'm correcting the notes at the moment, f of z is equal to I over z plus I, yeah? Minus I over z minus I, yeah? Or did I make a mistake here?
I feel like I should work it out, but,
Hmm.
you get 2I on the top over Z plus I
Mm-hmm.
This is not correct.
Oh, this is not correct?
I got 2I on the top.
But when I multiply this times that, I get iz minus I squared. This times that, I get iz plus I squared, but the minus gives me minus I squared. I get 2. When I got 2 over z squared plus 1.
I squared minus ZI squared. I might just be doing bad algebra.
So when I make a common denominator of these two, I get I times z minus I times z plus I. But this gives me iz minus iz to cancel. This gives me minus I squared minus 2I squared. Minus 2I squared is 2. So this is 2 over 1, z squared plus 1. So it checks. All right. Okay, so here's the thing. If we're going to integrate over, let's say, gamma epsilon of I, right, of, say, 2 dz over 1 plus z squared. Well, we can look at this as what? This is really the integral over gamma epsilon of I of what? Of I dz over z plus I minus the integral of I dz over z minus I, right? And one of these integrals is 0 by Cauchy's theorem. Which one is it? Let me introduce another, let me say G1, or yeah, this is, say, let's say F1 rather, F1 of z I over z plus 1, plus I rather, F2 minus I over, z minus I. Which one of these has trouble on the circle centered at I?
The first one.
Yeah, the first one?
Sorry, second one.
The second,
I minus I 0.
Yeah, exactly. The second one's got trouble because at the center of the center of the circle centered at I, we get division by 0, right? So this is, this is not holomorphic on the disk, the closed disk of radius epsilon centered at I. So this is the disk of radius epsilon, closed disk of radius epsilon centered at I. And surely this is not holomorphic on that disk because at the center we get division by 0, right? But on the other hand, this one is holomorphic for, modulus of z minus I less than or equal to epsilon, right? It is holomorphic on that disk. And so by Cauchy's theorem, the first integral is what? 0. So this is just 0 by Cauchy's theorem. And how about the other one? So we've got minus I integral of dz over z minus I. So last class, we proved that if we take the minus 1 power of z minus z naught and we integrate around the circle centered at z naught, counterclockwise fashion once, we get 2 pi I. So that gives me minus I, so the minus I from out front, and by last class, that's 2 pi I. So apparently this gives me give me 2 pi. So let's see here. By the way, this is holomorphic, right? So we've done the integral. But I'd like to point out to you something. We can actually write a primitive for the first piece. What's the antiderivative of 1 over z plus I on this circle?
1 over z plus I.
Yeah, like f1, we could say f1 of z would be, how about this? I log of z plus I. Why would that be okay?
Oh, because log is defined in the boundary.
Yeah, so the way to picture this, right? Log of z plus I, if I want to picture this one, so here's the I, right? Here's minus I. Where is this primitive in trouble? Where's the branch cut for that? There's a discontinuity for the log here. See, because this one's centered at minus I. Because we have to think about z minus z naught for the center. So plus I means it's centered at minus I. So you get into trouble trying to use the principal logarithm if you cut through this line here, right? But as long as epsilon is sufficiently, as long as epsilon is less than 2, we're okay, right? We haven't cut through the branch, and so that's a primitive. So another way of looking at this, why is this integral 0? It's because we have an antiderivative for it. We integrate around the loop. Fundamental theorem of calculus part 2 gives us that integral is 0. That's another way to look at it. These are not disjoint tools. Cauchy's theorem, fundamental theorem of calculus part 2, these go together, right, logically. So what happens when I try to integrate this function over the other circle?
Well, it's outside the boundary.
Excuse me. It also have to go to 0?
Yeah, because,
Well, the integral wasn't 2. 0 was 2 pi, wasn't it?
oh yeah, it's 2 pi.
So let's work it out. Integral over gamma epsilon minus I. This time let's look at the circle centered at minus I of, f of z, 2dz over 1 plus z squared, yeah? So we're looking at the integral over the circle centered at minus I radius epsilon of the first thing was what? I dz over z plus I, yeah? Plus the integral over the circle using our partial fractions decomposition here of, well, minus, right? Minus I dz over z minus I, yeah? So I would point out that, the F2, I'm calling it F2, F2 of z equals minus I over z minus I has antiprimitive minus I log of z minus I. And where is that defined? Here's a picture. Where does z minus, log of z minus I, that's centered at I, right? So the branch, the thing we have to be careful of, the discontinuity, and discontinuity spells disaster for differentiation, right? Differentiability implies continuity. So if you have discontinuity in the log, it can't very well be differentiable there, can it? Okay, so if it can't be differentiated, it's not a very good antiderivative, right? So this guy, F2 of z, it breaks down at that branch. But if we're looking at gamma 2, we're looking at the circle down here, aren't we? Right? So we have a primitive. You see the situation here. We have a primitive for half of the integral, and then we have a primitive for the other half of the integral. We can't have them both at once if we're on one of these circles, because each one of these circles gets in trouble with either F1 or F2, so to speak. And it's not like an insurmountable trouble, right? We worked out the trouble last time. It's 2 pi I. So which one of these integrals is 0 then? So this, the point is, F2 is holomorphic, right? So in fact, F2 of z is holomorphic on the disk of radius epsilon centered at I. Which means that, what does that mean? Among other things, it means it has a primitive on that disk. In fact, there's the formula for the primitive, right? I can do better than just write the integral formula like in Ftc One. I can give you straight up, there's the formula function which differentiates to give you minus I over z minus I. And so then, of course, by Cauchy's theorem, the integral, this one here, is 0, right? Or you could go back to any number of those theorems we talked about before, but Cauchy's theorem says that's 0. What's this other one? We've got what? I times what? Nope. This is I times the integral of dz over z plus I. And you're looking at modulus of z plus I equal to epsilon in the language of last time. We proved that that kind of integral, z minus, blah, blah, blah. Yeah. That we worked that out last time. That's 2 pi I. That integral is 2 pi I. Last time we proved this. The integral over the modulus of z minus z naught equal to r of dz over z minus z naught is 2 pi I.
Oh, yeah.
And so I'm just applying that result in the case z naught equals to I or z naught equal to minus I. In this case, z naught equal to minus I. So we get I times 2 pi I. In other words, we get minus 2 pi. So that's interesting, right? If we encircle I, we pick up 2 pi, right? If we encircle minus I, we pick up minus 2 pi. So what would happen, if we were to, what would happen if we were to look at this path, for example? All right, counterclockwise path, right? And suppose it's got I and minus I in it. What would be the integral of f of z dz? Words. 2 dz over z squared plus 1, yeah? If I'm doing it over this curve.
Oh, well, you could just take both of these together, right?
Why? Why can we take both of these together?
Because now we have a boundary that encircles all of it.
Yeah, but those two circles are not that thing, are they?
No.
So how do you get from one to the other? Yeah, what's the logic?
Okay, we're trying to do this on C. Can we straight up say, oh wait, no. But we still have discontinuity at 2 points.
Well, how about this? Here's 2 steps. Number 1, you can take this curve, right? And you can continue, and you could pinch it down to this curve, like this, right? We could squeeze that until it was like this, right? So this is, so we're going like this, right? And then apparently like this, and then like this, like that. And why can I say that, let me call that C prime. Why can I say that the integral over C and the integral over C prime is the same? When are we allowed to deform the integral of a complex function from one curve to another? What do we need to be true about the function between the curves to not get in trouble. We need that the function's holomorphic, right? So is this function, is 2 over z squared plus 1 holomorphic? Well, yes, it is everywhere except for these troublesome points, plus or minus I, right? So we can deform that peanut-shaped thing to almost like a figure 8, right? And then we can take the c prime, the integral over c prime, and we can deform each. We can obviously the integral over c prime is going to give you what? It's going to give you the integral over the upper loop and the integral over the bottom loop, right? So let's call those integral over c prime plus the integral over c prime minus. Or we could say north and south. How about that? North, south. I hope that makes sense to you what I'm saying. So like this piece, this piece and that piece. Are those, okay, so then it's clear that you can deform those to a circle of radius epsilon centered around those respective points, right? So we can say, well,
So when you're deforming, like what makes you be able to pinch at that point so you can cross over those loops? Like I don't get that.
why, that's I just decided to pinch it down so that I could change this peanut-shaped thing into a figure 8, and so then make this separation. I'm allowed to smoothly deform a curve into another curve provided they're holomorphic between each other. The integral. That's the deformation theorem.
Yeah.
So 2 dz. Now again, if they're not holomorphic between the curves, then we're in trouble. And so the top one. But the thing is that counterclockwise? It is, right? So the counterclockwise, which I called gamma epsilon of I can deform the top one to that, and I can. How about the bottom one?
Is it also counterclockwise?
Is it? Oh, it is. Okay, cool. So we have the rather unexciting answer that the integral is what?
What I said in the meeting.
Which was what?
2 pi and 2 pi.
Yeah, well, it's 2 pi. This one, we worked out the integral of the...
2 pi, the other one's minus 2 pi, which equals 0.
Mhm. Yeah.
Right.
Yeah, 0 is usually a good guess, right? But that guess for you was just hogwash if you don't know these things. I mean, it's a good guess, but yes. So deformation theorem. So you start to see that there's a strategy for calculating complex integrals, which is we find out places where the complex quantity has a divergence, and then we need to kind of like encircle those, figure out what the integral is around those divergences, and kind of piece things together from there using this deformation idea. So there's a lot in this example. Yeah. There is a way to make what I have in the notes right. So let me fix my example in the notes right quick. So in my notes, I claim that f of z is 1 over z plus I plus 1 over z minus I, right? So to make that correct, I just work backwards. Like what my notes is actually about is not the function that I claim, but it's actually about this function, right? So my notes are okay if everywhere I had 1 over z squared plus 1, you just replace it with 2z over z squared plus 1, because this is the partial fractions decomposition for 2z over z squared plus 1, actually. I am surprised I have not had a student correct this already. Maybe they did. You know, sometimes students make corrections and then they get lost in my email. So let's hope for that. That brings us to Cauchy's integral formula. All right. So I'm going to state Cauchy's integral formula for you, and I'm going to show you an example of it, but we won't prove it today, okay? Actually, I'm going to be greedier than that. I'm going to state for you Cauchy's generalized integral formula. So this is one step further. And here's what it says. It says that the mth derivative of z is equal to m factorial over 2 pi I integral over the boundary of d of f of w over w minus z to the m plus 1 power dz. So Cauchy's integral formula just says this: f prime of z is equal to 1 over 2 pi I integral over the boundary of d of f of w dz over w minus z, I think. Wait a minute. Uno momento. Oh yeah, there's no prime. There we go. So this one right here is just Cauchy's integral formula. I can't spell Cauchy. So Cauchy's integral formula is like m equals to 0. The generalized formula is up above. So here's an example. Integral over the counterclockwise oriented circle of radius 2 centered at the origin of sine of 2z over z minus I to the 6th power, dz. Oh, that's a w. Yeah? Was that the question?
No.
My apologies to the people not with us. They didn't miss too much yet, though. What is it?
We were just calculating this.
Yeah, let's calculate this integral using this.
But you have another key.
We've got this theorem to work with here. Yeah. And so what is it? It is 2 pi I divided by, listen, if I made this w instead of z, maybe it'd be easier to see. W,
No, you're fine there.
w,
So would
w,
we have
w.
m's equal to 5, right?
M is equal to 5, so we have 2 pi I over, so I'm solving this theorem for the integral, basically. 2 pi I, and then I'm supposed to do what? The ddz, ddz, the how manyth? You said 5? Yeah, 5. The fifth derivative of, apparently, sine of 2z, evaluated at what? Z equal to I, right? What is the fifth derivative of the sine?
That'll get you cosine.
Cosine with a plus or a minus.
Well, you go around once, so.
And 2 to the 5th power, right?
Yeah.
So let me track it for us. Sine, I'm using my fingers. Sine goes to cosine, differentiates to minus sine, differentiates to minus cosine, differentiates back to sine, cosine. So I think we're plus cosine.
I was doing it by cycles.
So cosine of 2, and then z, but we put z equals to I.
What is that? That says,
Oh, you know that.
yeah, so if you're up here, that means you're 1.
So this is, what do we got here?
Some are 0.
We've got 2 pi I times 2 to the 5th, right? Which is 2 times 2 times 2 times 2 times 2 over 5 times 4 times 3 times 2. That's Kosh.
Yeah.
The 2's be canceling. This 4 gets rid of 2 of the 2's. So you got 8 pi I cosh 2 over 15, obviously. There you go. I've got a minus. I somehow think the derivative's negative in the notes. Is the fifth derivative sine minus cosine? Am I wrong?
I don't think so, because if you do 4 derivatives, that's one cycle. It gets you
Yeah.
where you started.
Yeah, I think the notes have a sign error there. So I think we should get 8 pi I cosh 2 over 15.
Because you go, yeah, if you start at sine, right?
So, do you guys, all right, so like think about this. What if we were to calculate this directly in terms of the definition of the complex integral we shared earlier, like a couple classes ago, right? You'd put x equals to 2 cosine t, y equals to sine 2t. You have to work out like the real and imaginary parts of this, plug it in. It's quite horrible. I mean, this, and it's actually instructive to do that. You can you can like work this out and figure out, this is a pair of real integrals. Like you can calculate the imaginary part of this and the real part of this, and you're calculating the integral of the real part around that circle plus I times the imaginary part around that circle. This result actually then means that the integral of the real part is 0, and the integral of the imaginary part happens to be 8 pi cosh 2 over 15. This is even uglier if you look at what it means in terms of the real integrals that underlie this problem. But already I think you see why Cauchy's generalized integral formula is like a very, very powerful tool, right? Anyway, that's where we're going. And actually the proof of that's not too hard. It's related to the homework problem you guys worked, believe it or not.